Hello there and welcome back to this video series on control systems. Over the past few videos we have been seeing Nyquist criterion, and we have seen an example to illustrate the application of Nyquist criterion. It is shown that from the open loop transfer function, closed loop stability can be predicted, and we have also seen that it leads to Bode plots and other design tools, as we will be discussing at a later time. As a prelude to all that, we will try to define what is a minimum phase transfer function and how the Nyquist criterion simplifies in the case of minimum phase transfer function. First, we will define a minimum phase transfer function, which we abbreviate as MPTF. This is a transfer function that does not have any poles or zeros in the right hand side of imaginary axis. If a system is having MPTF, that is minimum phase transfer function, the Nyquist criterion can be simplified very greatly. We have seen that in the case of Nyquist criterion, there are 4 segments or 3 segments. C1 along positive imaginary axis, C2 is a big circle, C3 is negative imaginary axis, and C4 is the small circle, and we draw the Nyquist plot for each of those segments. But if the transfer function is minimum phase transfer function, it is just sufficient to draw the plot for s is equal to j omega as omega varies from infinity to 0. That is, for only one segment you will draw the plot, and the criterion also is very simple. If the plot you generate for s is equal to j omega to as omega varies from infinity to 0, and such plot encloses, see, I have written in big letters, bold and underlined. We are not talking about encircled now, it is encloses. Recall the definition of enclosed as we discussed in the previous videos. A point is enclosed by a curve if it is found to the left while you are traversing along the curve. We'll try to explain what this means. We'll try to explain what this means in the next slide. Let us say you have a minimum phase transfer function system given by k times x of s, and we try to draw the Nyquist plot for s is equal to j omega as omega is varied from minus infinity to 0. This curve is plotted. Let us say the curve appears something like this. If you imagine yourself walking along this curve, this point minus 1 is lying to your right hand side. So the critical point minus 1 j0 is not enclosed. Let us slightly increase the value of k, make it k is equal to k2. The point of intersection slightly moved towards this minus 1 point. As you keep on increasing the value of k, the point of intersection keeps on moving closer and closer to the point minus 1, and at some value of k is equal to k3, the point of intersection exactly coincides with the point minus 1 j0. For value of k is equal to k3, we say the system is marginally stable. Any further increase in the value of k, if you make it k is equal to k4, then if you walk along this path, the minus 1 j0, imagine yourself standing and walking along this, you will find minus 1 j0 to your left hand side, and if the point is towards the left hand side, minus 1 j0 is enclosed, and thus the system is unstable. So two things we'll see. As k is moved from k is increased from k1 to k2 and further, the point of intersection of the Nyquist plot for s is equal to j omega, omega varying from minus infinity to 0, it is moving closer and closer to this critical point minus 1. That is why I left it blinking there. Clearly see what we are talking about. Let us say this is the graph for k is equal to k1, and then let us say this is the graph for k is equal to k2. As you keep on increasing the value of k, the point of intersection moves closer and closer to the critical point, and at one value of k it passes through, and any further increase will make the curve to enclose point minus 1, 0. At that point the system becomes unstable. So for all values of k, when the point of intersection lies between 0 and minus 1, the system is stable. When the point of intersection crosses this minus 1 point, if it lies anywhere in this region, the system is unstable. So this is marginally stable, on the borderline of stability and instability. That's why we call it a critical point. We are going towards the direction of defining what we mean by gain margin and phase margin. Let us say your open loop transfer function f of j omega is k1 times g of j omega h of j omega, and you draw the plot, and the point of intersection is A, and we say that if the point of intersection is very far off from this critical point and close to the origin, we say the system is very stable. If it is very close to minus 1, it is very unstable. It is coming closer and closer to instability. In the limit, when it crosses this critical point minus 1, the system becomes unstable. The frequency at which the graph crosses the negative imaginary axis is called phase crossover frequency. See what is happening at phase crossover frequency. The angle is the angle of the line going from O towards A is minus 180 degrees. Okay, that's why we are interested in the point of intersection with minus 180 in body plot. The line going from O to A is minus 180. We will define gain margin. The distance OA from O to A is a measure of stability. Okay, let us say when k is equal to k1, the point of intersection is at A. When k is equal to k3, the point of intersection is at C. So we can write OC by OA. You can see that the length of this line from O to C is 1. OC divided by OA is 1 over A. So you can say K3 is equal to K1 into 1 over A, that is K1 into X. So what this means is, if the system has an open loop transfer function of f of j omega is K1 times g of omega, j omega, h of j omega, I'm sorry, j is missing here, then increasing K1 by a factor of X, the system becomes marginally stable. When we say it's marginally stable, when the curve passes through the critical point. This quantity X is called gain margin, 1 over the distance OA. We'll further examine this, okay, to see what we mean by gain margin. We saw that the frequency at which the curve intersects with the negative real axis is called phase crossover frequency. At this point, phase is the angle made by the line segment going from O to A. That is the line that is at this point, it makes minus 180 degrees. So phase crossover frequency can be obtained by equating g of j omega, h of j omega to minus 180 degrees and solving it. That will give you omega phi. And gain margin is given by 1 over this. So you find what is phi? substitute here, you get gain margin. Of course, gain margin often is expressed as decibels, that is take logarithm to the base 10 of this x and then multiply by 20 log to the base 10 x. We'll be interested in two other quantities, that is gain crossover frequency and phase margin. We will see that. Let us say this is the curve for some value of k is equal to k1. We will consider a unit circle. This circle has a radius of 1 and find what is the point of intersection occurring here. This point, let us say, is G. This G is what we call gain crossover frequency, the point where this curve intersects the unit circle. So at G, the magnitude is 1 because it is on a unit circle. So G of j omega g, h of j omega g, magnitude is equal to 1. And the phase margin is 180 degrees plus G of j omega g, h of j omega g. We can give perhaps a physical interpretation if there is excessive time delay, pure time delay, that is dead time as we call. When the dead time increases, this curve rotates about the point O, as you can see here. I'll just show it once again so that you can see the curve is moving. You can see, okay, that is the point of intersection, and the curve rotates and passes through the critical point. The angle through which it moves, represented by this angle, is the phase margin. So two things, gain margin, phase margin are the margins. Gain crossover frequency, phase crossover frequency are the frequencies. The idea is, if the gain margin of a system A is double that of system B, and in some sense we say that system A is double as stable as system B. So this gave a kind of a measure using which we can judge the stability of two systems and say that one system is more stable or less stable than the other system. We'll solve one problem, very quick problem, and close this. We'll solve one very small problem here and close this topic. Let us say you have a transfer function as given here. Like in all frequency response problems, you say S is equal to j omega. So you have g of j omega, h of j omega is k e to the power of minus 0.2 j omega by j omega into j omega plus 4. Notice that this term doesn't contribute anything to the gain, because e power j theta is cos theta plus j sin theta. Its magnitude is 1. Cos square theta plus sin square theta is equal to 1. Okay. What we are given is what is the frequency at this critical point, at the point where the system passes through the critical point. He is asking what is the value of k at which the sustained oscillations occur. When this curve passes through the critical point, sustained oscillations occur in the closed loop system. So at this point, OC is equal to 1, that is g of j omega phi, h of j omega phi is equal to 1. So k by all this is equal to 1 and k is equal to 22.2. It is a very small silly problem that tries to illustrate that this minus 1 j0 or minus 1 plus j0 point is a critical point, and when the curve passes through that point, we say sustained oscillations occur. A more challenging, a little bit more difficult problem is it possible to solve this problem if this omega phi is not given? That would be very interesting to see. Try it when you're free. So important to note, gm has to be positive and this phi m has to be positive. We say if more is the gm or phi m, the more is the stability of the system. Important thing to notice, if there are more than one gain or phase crossover frequencies, it is better to draw complete Nyquist plot and decide. With that, we will provide the summary here. Minimum phase transfer functions do not have any poles or zeros on the right hand side. For MPTF, the Nyquist criterion is greatly simplified. You draw only for one segment, that is S is equal to j omega, omega varies from infinity to 1, and we will now see that critical point should not be enclosed as the criterion, and gain margin is the amount of additional gain that can be included in the system to cause sustained oscillations. We don't want sustained oscillations. So we'll see what amount of additional gain can be induced and yet maintain system stability. So gain margin and phase margin are measures of stability of minimum phase transfer function systems. That's all we have for now. Have a great day.